So now, a very important step. We want to make puzzles that are fun for humans to solve and that are graded for difficulty. How can we grade for difficulty? In the last video, I showed the one somewhat useful measurement we can get from our OR tool solver, the branch count. I know from personal experience that the branch count is not a very reliable indicator of difficulty. I know that most super easy puzzles have a branch count of 0, but so do plenty of difficult puzzles. Ultimately, the problem is that OR tools and any brute force constraint solver does not solve puzzles in a manner that remotely resembles how we, as humans, approach the problem. This is why I advocate for using a different approach. We can make a solver which gets a little closer to what a human does, and we definitely can produce a more reliable difficulty metric. It's not going to be perfect, can't be perfect, but it will definitely be better. My approach is to write a solver algorithm that uses similar strategies to what I personally use when solving each puzzle. In order to do that, I need to actually solve some puzzles. And I need to take extensive notes about what I'm doing. What patterns am I observing as I solve the puzzles by hand? I build up a catalog of strategies, first on paper, taking screen snapshots and extensive notes. Are your rules different than the ones I'm about to use? It's possible, probably likely. I'll start with the easiest rules from my point of view. These easy rules will come into play for all puzzles. For the easiest puzzles, they're the only rules you need. I often find that rules tend to come in complementary pairs. Here's the simplest two rules which form such a pair. If all the mines have been found in a container, we can eliminate the remaining cells. If all but 3 cells have been eliminated in a container, we can place mines in the remaining cells. By the way, there's a very similar pair of rules which involves looking at clues, which are essentially complete. I'll discuss that one a bit later in the video. This rule just looks at containers, not clues. Note that a production rule consists of a pattern that we're looking for and an action to take when the pattern is observed. It's fairly common to leave out crucial details when expressing these rules for the first time. We tend to assume a lot of things that need to be coded explicitly. As I code these rules, I'll quickly learn what I'm omitting because the code will break, and then I'll fix it. It's good to document the rule accurately as best you can. Let's call these two complementary rules, collectively, the rules of easy container cleanup. A puzzle that can be solved with only those two rules is super easy, and it's highly unlikely that any such puzzle exists in the test suite that we made, since when we made that, we used a brute force solver and we eliminated as many clues as possible. Now, a puzzle that just uses these two rules, a super easy one, can almost always be made more difficult while still having a single solution by removing an additional clue or two. And my brute force solver, which aims to minimize the clue count, is going to do that. Puzzles that can be solved with just these two container cleanup rules are going to have a much higher clue count on average, although clue count alone is not a reliable indicator of difficulty. Before coding these two easy rules, let's modify the generator and the solver we wrote to be able to support multiple solvers. Since I still want to support the original OR tool solver occasionally, I'm going to modify the generator and solving scripts to support using either one. I do this by adding a -s solver command line and loading the solver function dynamically. The new solver will be called solve PR, PR standing for production rules. I used -SOR when I want the OR tool solver and -SPR when I want the new one. I'll use the import lib library to dynamically load the solver I want. If we use the production rule solver, we'll get better ranked puzzles that are more suitable for humans. Our new solver won't be able to solve many puzzles at first, but eventually, as we add rules to it, it will only be able to solve puzzles that are suitable for humans. The new PR solver is going to contain a list of our production rules stored in an array. Each rule has a solving function, which returns true if the rule makes progress on the puzzle. The solving function looks for the pattern and applies the action if the pattern matches. That action is typically setting a currently unknown square on the board to empty or mine. In the list of rules, we provide the solving function, a score for the rule, which is a measure of its difficulty, and a tier number, which is a related concept. I'll talk more about scores and tiers in the next video, where I focus on different methods of difficulty estimation. But in brief, the score is an estimate of the difficulty of the move, kind of similar to how pieces are scored for board evaluation in chess. In chess, a rook is worth 5 pawns and a queen is worth 9 pawns. Our easiest rules are like pawns and will have a score of 1. More complex rules will be scored relative to that. So if the rule feels 10 times as hard as an easy rule, it gets a score of 10. This measurement is very subjective, of course. The tier number is an ascending number that corresponds to what kind of puzzle difficulty we can expect for a puzzle that requires this rule. So our easiest rules are 1, the medium rules are 2, and the hard puzzle rules are 3, and so on. When we generate puzzles, we can limit the rule set we use to a maximum tier, which will enable us to force the generation of easier puzzles. Similarly, we can specify a minimum tier requirement and throw out puzzles that don't require at least some advanced strategy to solve. These 2 easiest rules that I've discussed so far, the container cleanup rules, will get a score of 1 and a tier of 1. Over time, we'll add more complex rules with higher scores and higher tiers. The solver will walk through the list of rules and try each one in order. If the rule makes progress, the solver will start again from the top, from the easiest rule. This ensures that we don't attempt a more advanced rule if an easier rule has not been tried first. This way, if I'm keeping a record of the strategies used, I'll know if a puzzle can be solved without invoking more advanced strategy, meaning it's an easier puzzle. During the loop, if a rule fails to make any progress, we advance to the next rule, trying successively more and more advanced rules. If we make it through the entire list of rules without making any progress, we consider the puzzle unsolvable. This doesn't mean the puzzle is unsolvable, but that our production rule solver can't solve it. If we can't solve the puzzle, and our production rule solver is well written, it means the puzzle is probably not suitable for a mass audience. Now, there are a small number of people who enjoy trial and error solving. I've corresponded with some of them. I personally find it tedious, so I try to avoid making puzzles that require it, but there is an audience for that. Now that we have the solving algorithm in place, let's make some useful data structures for the production rules we will soon write. These rules both involve looking at counts of squares in containers. So we want to make a loop that tries each container in order. To do this, we'll want a data structure that represents the board of cells and a list of containers, each container being a list of cell addresses. When the solve begins, I'll set up a board object which contains a cell dictionary, and I'll also set up a list of clue addresses, and for each container, a list of its cell addresses. For each clue, I'll pre-compute its list of neighboring cells, since we'll be interested in those. I'm going to make all my production rules members of this board object so they can easily take advantage of this pre-computed puzzle representation and utility functions, which I'll write as we go. One thing I've changed in the code since the last video is how I deal with the 3x3 blocks in the puzzle. For both solvers, I am now using a layout string to identify the block containers of the puzzle, rather than doing the explicit math to compute 3x3 blocks. This is a little future-proofing to make it easier to get the constructor and solver to work with more arbitrary jigsaw-style layouts, which we'll use in a future video. Now let's begin to code the rules, finally. For the container cleanup rules, I'll loop through each container. For each unsolved container, we'll obtain pertinent info using a useful utility function, unsolved containers, that we'll use elsewhere. That function internally uses another function called split cells by value, which divides the cells of the container into 3 groups: unsolved, mines, empty. For pretty much every rule, we'll be interested in those 3 partitions. If there are no unknown cells, we'll skip the container entirely. Now, the heart of the rule, if there are 3 known mines, we can eliminate all the unknown squares in the container. Here you can see that happening in row 2, which already has 3 mines, as well as a 3x3 block on the upper left corner, and row 8. Contrariwise, if there are 6 empty squares, we can place mines in the unknown squares. In either case, the container is now finished. Here I'm placing the remaining mines in the 3x3 center block, as well as column 6. This rule basically supplies the necessary cleanup work for an already solved container. Now, you may choose to retain more information about your cells and containers, such as these splits, rather than recomputing them each time you run a rule. It's more efficient that way, but it's also easier to introduce bugs if you don't accurately update your counts. As we go through the container loop, we may get more than one hit on this rule. If we're not careful, this may cause us to make second-order solves, deductions based on eliminating a square from an earlier iteration of the loop that would not have been readily apparent before the loop started, before making all the available first-order solves. Now, it's okay to do this, but it does affect solve order in a potentially counterintuitive way, and it reduces the number of solving steps and the difficulty score of the puzzle. So I like to avoid it. To avoid second-order logic, you can make a list of found deductions, but then you don't act on them until you've executed the scanning loop. So you essentially have a separate scanning loop and then acting loop. This will ensure that all first-order solves happen before second-order solves. It's a bit like delayed gratification. Take this puzzle, for example. I've done 2 different solves on it, one in which second-order logic is allowed, and one in which it isn't. When delayed gratification isn't used, you can see a mine being detected here that was not immediately apparent at the end of the prior step. It wasn't apparent, but it found it within the same loop by first solving this row before looking at this block. In this case, delayed gratification causes the puzzle to take 18 steps to solve instead of 16. And now I'm going to stop saying delayed gratification. This is a subtlety that maybe isn't super important here, unless we are intentionally keeping track of solve order. This kind of thing becomes more important in more advanced rules. In those cases, I usually try to avoid second order logic because it can create a very counterintuitive solve order. So after the loop, we'll call functions for eliminating squares and setting mines based on what we've discovered. These functions should only return true if actual progress is made on the puzzle. If I make the same deduction twice, I want the second attempt to fix it to return false so we don't mistakenly believe we've made progress. To avoid an infinite solving loop, we need to be able to accurately detect when we haven't made genuine progress. Also note that this type of solver, production rule solver, as I'm writing it, is incapable of solving puzzles with multiple solutions. It is only checking rules that have a definitive solution. So if a puzzle has multiple solutions, these rules would never succeed in solving the puzzle. Now that I've implemented these rules, I want to check to see if any of our test suite puzzles are solvable with just these 2 super easy rules. At this point, it's advisable to start making use of the provided solutions in the test suite. If we're testing a solver, we want to make sure that there are no false positives, that it's not providing a solution or even making a bad deduction that is counter to the known solution of the puzzle, and we want it to fail as quickly as possible when that happens. To do this, I optionally load the known answer to the puzzle, and when eliminating squares or placing mines, I check against the provided solution and raise an error if it doesn't match. This makes it easier to catch bugs as we make our rules. Now, I'm not going to be doing this when we're generating puzzles because I don't know the solution. But when we are writing our solver, we'll use our solving script, and that will always load in the correct solution because the purpose of the solving script is to test our solver. As the rules get more advanced, you'll find it's very easy to overgeneralize them when coding them, which can make false positives occur. While it's possible to vibe code your rules, I don't think it's advisable to do so, since in August of 2025, there's a very high chance of error in the resulting code. I do use cursor autocomplete to detect symmetrical things as I write the rules, but I'm careful to check the code for accuracy. I'll also turn cursor off if it's making a lot of stupid autocomplete suggestions, which happens. It's a little safer to use AI features after you've already coded a few rules yourself, because then the approaches you're using are visible in the prompting to the AI and it can mimic your style better. Now, if you've been paying attention, you know there's two more super easy rules to add, which form another complementary pair. And that pair in turn complements the first pair. We've added a rule for easy to finish containers, two rules, but it's also important to look for easy to finish clues. Clue squares can be easy to finish in two ways. If we've already identified the mines, we can eliminate all the other unknown neighbors. Here I'm doing it in 4 places, for the 1, the 3, this other 1, and this other 3. The complementary idea is that if the number of unknown neighbors is small enough, if it's equal to the clue number minus the number of already placed neighboring mines, we can place the remaining mines. Here I'm doing it for the 5, the 4, and the 2 in the lower right corner. These things are definitely easier to visualize than to describe in words and or mathematical language. This is very similar to the logic we're using for containers, but instead of the mine count being fixed at 3, as it is for containers, it's set to whatever the clue is, and we only care about neighboring squares. I'll call this rule Easy Clue Cleanup. It'll make use of an unsolved clues function, which works similar to our unsolved containers function, returning 3 arrays of neighboring cells so that we know which neighbors are unknown, mines, or empties. Whenever this function yields a result, the clue has at least one unknown square. We're going to use this function a lot, both unsolved containers, unsolved clues. We are usually only interested in those, but if you happen to be interested in the solved ones, remember that this only returns the unsolved ones. The inner logic is similar to the container cleanup rule. If the number of mines is equal to the clue, we can set the unknowns to empty. Else, if there are a sufficient number of empty squares, we can set all the unknowns to mines. In either case, the clue is finished and we're just doing cleanup work. Note the twin structure of these 4 rules, which I've coded as 2 functions. The clue rules complement the container rules, and each branch has 2 complementary rules which mirror each other. This is a very typical structure that I encounter when generating rules. Now that I have these 4 easy rules, we can check to see if any of our test suite puzzles are solvable. Nope, not yet. As I suspected, there are no puzzles in my brute force test suite that are solvable using just these 4 rules. However, I can generate new puzzles that can be solved using just those 2 rules. On the command line, I'll rerun the generate command and I'll specify to use the PR solver and to only use rules with a tier of 1 or less. And this will quickly produce some super easy puzzles. A test suite of 1,000 super easy puzzles has an average clue count of about 16.36, which is definitely higher than the average clue count of the brute force test suite, which is 13.13. When I test the standard puzzles on J.K. Dewar's Blueberry Trio site, I find that these 4 rules are sufficient to solve every single one of his standard puzzles that I've tried. So by that metric, none of the puzzles in my brute force test suite are standard puzzles. Also look at the work number on the puzzles. This is our first measure of difficulty based on human style solving. It's a sum of the scores of the rules used to solve the puzzle. As easy as these puzzles are, some are just slightly easier than others according to the score. They are essentially a count of the number of times the solver needed to context switch. Again, I'll talk more about difficulty measurement in the follow-up video. There's a lot to it. Now, an interesting question. Do any of these super easy puzzles, the ones that can be solved just with easy cleanup rules, do any of them trigger a non-zero branch count in OR tools? The answer is no. I haven't been able to find a super easy puzzle that triggers a non-zero branch count. So a non-zero branch count tells us it's definitely not a super easy puzzle. But are there any 0 branch count puzzles in our randomly generated test suite that can't be solved with these 4 simple rules? Hell yes. All of the 0 branch puzzles in the test suite, over 500 of them, meet that description. They have 0 branches and they can't be solved with these 4 rules. And that, my friend, is why you shouldn't use branch count alone to rate the easiness of a puzzle. It's simply not a reliable indicator, just like clue count is not a reliable indicator. Moreover, many of these zero branch count puzzles, about 35% of them, can't be solved, by me anyway, without brute force, even with more advanced rules. They are not all suitable for humans, in my opinion. Since puzzle 2 isn't solving yet, let's see why. At this point, I'll add a step visualization argument, -ds, which draws an image of the puzzle for each solve step. For each rule that gets hit, we output a picture of the puzzle and the partial solution, distinguishing between unknown and empty squares. We'll also show the name of the last rule that was used. And that way we can see how far the solver got and approximately which order it solves the puzzles in. As each step makes progress, I'll highlight what the changes are. This will be incredibly useful for debugging and understanding the interplay between the rules we write. But let's not get ahead of ourselves. How are we doing with puzzle 2? When I output the debugging steps, I get one drawing. We're not getting very far. And that's because we need to do something a little more complicated on the very first step. And we haven't coded anything but super easy rules, cleanup rules. In puzzle number 2, and in many randomly generated puzzles of this type, we can't use those simple cleanup rules right away, but we can exploit what's going on with that 3 in the corner. The 3 is going to need 3 adjacent mines, isn't it? So any cell in the block that is not adjacent to the 3 can be eliminated. We need a new rule for that. I'll add it, and I'll call it the medium rule of greedy clues. Since it's not quite as straightforward as the first rule, I'll give it a score of 2 and a tier of 2. I call this the medium rule because I described it in an overly specific way, a simple version of the rule, where I essentially just look for a 3 clue that has neighbors that are all in one container. I can also imagine a more sophisticated, generalized version of this rule, one where I take into account multiple clues sharing a container and examine them collectively, or clues that are not fully contained, but which have a limit to the number of external mines that can be placed. I think we'll eventually code 2 or more forms of this rule. The easier one we'll make first, and since it's easier to spot, it gets a low difficulty score. It's a medium. The generalized forms we'll try later, and those will merit a higher, harder tier since the patterns they identify are harder to spot. This is one of these situations, as a longtime coder, as someone who pursues elegance in my code, that is extremely counterintuitive. It may seem efficient to just implement a single grand unified solving rule that covers all the cases, but this makes it impossible to measure difficulty. It's not much different than using an SAT solver. So it's definitely better to have multiple, even redundant versions of a rule, easy to detect variance and hard to detect variance for more accurate difficulty rating. So fight your urge to be elegant during this part of the process. This rule, again, walks through the unsolved clues and skips the ones that don't need 3 mines exactly. And now it checks the neighbors against the containers. This is our first rule that takes both clues and containers into account and looks at the interactions between them. In this particular case, we're interested in the containers that fully contain all the neighbors to the clue. And then we look at those fully enclosing containers and check to see what's going on. Having added the simpler version of the clue, I can see now that 2 of our brute force puzzles can be solved. Finally, a hit. And a generated test suite of puzzles solvable by this rule has an average clue count of 16.12, only slightly less than without this rule. But again, there is a complementary rule to the greedy rule. What happens when there's a 1 in a container? I call this a pushy clue because it pushes mines away from the 1 and forces them elsewhere in the container. Pushy complements greedy. Look at the 1 here. It must have a mine and one of its neighbors in this 3x3 block. Otherwise, there will be insufficient room to finish that block. So it forces a mine in the remaining cell in that block and also allows us to clear its other neighbors. So I'll code a version of that rule, the pushy rule. Again, there's probably a more advanced, generalized version of it to come. So again, we walk through the unsolved clues and compare them to the containers. This time to containers they might be partially enclosed by, since a one clue can push even if it's also pushing somewhere else. For each such container, if the count of unknown non-neighbor cells is small enough that solving the clue provides the remaining mines needed to finish the container, we can set those unknown cells. We can clear its other neighbors. This brings the number of puzzles we can solve to 5. So now solving that makes some further progress, and that gets us to here on puzzle number 2. And I can see another deduction now. The upper 3 in column 3 has 2 forced mines. Because the open cells to the right of it can't hold more than 1 mine due to the 2 mines already in that 3x3 block. Also, because those 2 cells in column 4 are at most 1, we can place 2 mines in column 4. The container version strikes me as a little easier to spot, so I'll put it in the list first. After adding it, the number of solved puzzles in my test suite goes up to 8. Here's the rule of at most 1 containers. I'll let you decipher it. Then we add the clue version of this rule, the complement, which I will also mercifully skip explaining. But take a look at the bestiary that I'll be talking about in a minute. It illustrates all the rules. Notice how, as the rules get more advanced, the coding gets more difficult and subtle, and it's easier to introduce bugs. Also, the auto-completion suggestions from cursor can get pretty bad at this point, and I often find myself turning it off because it's making terrible suggestions. And that's because we're on the bleeding edge. Now, I can solve 26 of the puzzles in my test suite with this new rule, a bigger jump. Also, we can finally solve puzzle 2. Here's the final solve sequence. You may notice that the solve order is slightly different than the solver order I used when I was solving it manually. This solving algorithm is better than I am at spotting the easiest patterns, and it'll always do them first. I find that when I'm doing the Blueberry Trio puzzles, the standard puzzles, which I know are all solvable using just those cleanup rules, I will still use rules like these medium ones all the time just because I spot them first. Now that puzzle 2 is solved, I need to find some new rules. So the way I usually do this is I add a draw unsolved flag to my solver, and I have it print out any unsolved puzzles it encounters, each one showing the maximum amount of progress it was able to make. Then we'll look through those pictures for puzzles which are nearly solved, since those are good candidates for manual solving. It's the low-hanging fruit. Going through these, wow, 0 progress on puzzle 1, a little progress on 4, a little on 8, and a lot of progress on 10. Let's look at that one more closely. It looks almost finished. So notice how I was able to quickly zero in on a good candidate because of these pictures. Looking at the unsolved part, I can see that one of the squares underneath this 2 must have a mine, because that row 3, already has 2 mines, and those are the remaining 2 squares. And that means we can clear the neighboring cell to the 2 above those 4 cells in row 3. Here we have an at least 1 situation. Those 2 cells have at least 1 mine. It's a little different to the at most 1 rule, which we were just coding with the pushy rules. This rule is very similar to an at most 1 rule, but subtly different. My first implementation didn't match this pattern, so I used the verbose option on my solver to add some console debugging. I want to follow the progress when that target clue is evaluated. Sometimes I'll add a target address parameter, which turns on very verbose debugging when a particular condition is under consideration. After fixing the bug, we can solve puzzle 10, and our overall solve count went up from 26 to 32 or so. I think that's enough rules for now. This isn't so much about the specific rules as the technique of using rules in general. We definitely need to add some more, but I think you get the picture. In the code that's checked into the repo, I've added a few other medium rules, and I've added a tier 3 rule, which looks at least n and at most n subsets and how they interact in more subtle ways. It's closer to a grand unified rule of solving this puzzle, and it brings our solve count up from 32 to 519. which is half our test suite. The hardest puzzles it can solve are very hard indeed, and probably at the upper limit of what you should be publishing or I should be publishing, and far more difficult than what mainstream media publications are interested in. But they still don't require brute force. If there's enough interest, I'll put out an explainer video on that particular generalized rule. But it's in the bestiary. What's the bestiary, you ask? Well, as we add rules to the solver, and the rules get more difficult and subtle, we create a potential problem. If we go back and look at the code after a few months away, the reasoning behind the more advanced rules is going to be difficult to understand just by looking at the code we wrote. A lot of these rules make sense at the time you write them, but if you try to understand what they're doing from looking at the code alone, even a few days later, they can be pretty mystifying. I am reminded of the description of the Perl programming language as a write-only programming language. Advanced production rules can also feel write-only. They are much easier to understand if you have a visual reference to accompany them. To address this, I'll sometimes give the rules unique names, sometimes catchy names even, to help me remember what they do. And more recently, I've begun to visually document the rules in an illustrated markdown file, a kind of medieval bestiary of all the rules I've coded and maybe a few that I haven't yet. Each rule comes with one or two visual examples. This will make it a lot easier to understand the code when we revisit it down the road. Here's the bestiary that I've added to the repo. You can use the bestiary to view all the different solving rules I've added to the solver, including the ones not covered in this video. In the next video, I'm going to cover several different ways that we can use this PR solver to estimate the difficulty of the puzzles that we generate with it, or any minesweeper sudoku for that matter. Let me know in the comments if there's any particular topic you want to hear more about, and subscribe to the channel and hit the bell if you want to be notified of future videos. Happy puzzling!